direct imaging should be impossible. I mean, when I first learned about this, I thought there's no way you can actually take a picture of the planet because it's so dim compared to the star. And yet, they've done it. Now, they've done it in only a few examples. So it's like, what? When I first learned about this, I didn't believe it. So this is an example. This is actually one that looks like sort of the Eye of Sauron, if you know Lord of the Rings here. This looks crazy. But that's because they've done some heavy processing of an image. What they've done, they've tried to take a picture of a star, but they want to dim the light of the star. So they put something right in front. It's like if you're trying to look up at the sun and it's too bright, or you're trying to look up at the sky, I mean. So you put your hand in front of your face in order to block the sun. This is sort of what they've tried to do is here. So they don't worry about this thing right here. And don't worry about all these weird stuff here. That's just artifacts from all the heavy processing they did. But if you zoom into this little point right here, they took same sort of picture in 2004 and then in 2006. And this dot, though, did move. And it turns out they've done more data points. This thing is in a Keplerian orbit. In other words, it's in a sort of stable orbit. So it looks like they've actually taken a picture of this planet, which I didn't think that would ever be possible. Now, some scientists, of course, said there was problems with this method, that it actually is wrong, and then recently it's back in again. So first it was sort of, yes, it's a planet. Then some people said, no, it's not. And now it looks like, at least at the moment, it's back in. So it looks like this is really a planet. So this is sort of I think it's a crazy way. But I think it's awesome that they've managed to sort of really push the limits of what we can do with image processing. So don't worry about this. The star doesn't actually do that. They're just really playing with the data to sort of try to detect tiny little changes. Another method is called gravitational lensing. This is kind of neat. This uses the, well, we learned about this earlier in earlier videos. I talked about Einstein's general theory of relativity. And it says that if you're looking at the light from a star and something passes in front of it with lots of mass, it might actually lens the light of the star. And to lens it means it's going to, well, distort it, but also it can increase. So in other words, let's say you're looking at the light of the star, it looks like this. As this thing passes in front of it, it's going to sort of lens the light right here and sort of increase this light of the star. So it goes from this to brighter. And as it passes away, it goes dimmer again. Okay, well, that's just another star passing in front of a really bright star. Who cares? Well, we care because what if this lens star has a planet around it? So remember now, we're looking at the source star. This is the bright star. We're actually looking at its light. So from the Earth, we're always looking at this star. And what we do is, because this star right here passes in front of this star, it's going to lens the light from it. So we expect it to go sort of up like this over time. If this is the sort of, this is a graph of time, and this is the sort of, yeah, the brightness of the star, you'd see it sort of look like this, like small little thing. It goes bright, and then it goes dim again. And yet, if there's a planet there, it's going to make an asymmetrical shape. So in other words, instead of just going up and back down again, they look for a spike. They look for something that goes, whoa, like this. That tells you, aha, there's something asymmetric there. It turns out from the shape of that spike, they can tell lots of things about this planet that's going around the star. So this is some real data here that they used. For example, here's one of these. So it going up, then back down again. This is a lensing event. So there's lots of these. It's really funny. It's called Ogle and some of these things. And there's RoboNet. And so there's, for example, a group of Danes who are actually working on this, among a lot of other scientists. But what they've done is, of course, when they detect one of these, there's lots of sort of robotic telescopes that are always looking at the sky for this. When they see a lensing event, it sets off alarms, basically. So anyone who's sleeping definitely gets up and logs onto their computer to try to see what's going on. And when they see an event like this, they look for asymmetric, so either on the leading edge, but it's a lot easier to find the trailing edge because it's hard to detect when it's leading. People sort of have to start looking. Well, they normally start looking at this end, so they tend to detect them more on this side here. But if you look at this, look what happened here. They noticed a spike. And if you zoom into this, this is what happened. The data points with error bars, you can see them that they go up compared to what should have been down here. So from that, they've detected an exoplanet using that method. And finally, we have the radial velocity method. So this uses the star's sort of, I'm going to call it a wobble, to detect the existence of an exoplanet. Now this one right here, I'm not going to go over it in much detail right now because in the next bunch of videos, I'm going to go into this in very big detail. So we're going to sort of zoom into this method here, this radial velocity method. One last thing I want to show you though is this. I mean, they've been detecting hundreds of them. In fact, Kepler is adding a few thousand to the list very soon. So this is just, some of the data that I found recently, at least when I'm making this video. And I bet when you look at this video, that's probably changed. This is just an idea. Now, this is a logarithmic scale, but they look at the orbital semi-major axis. In other words, sort of how large the orbital radius is in astronomical units. So that means that something that's right here, this is like the Earth. The Earth orbits at 1 AU, which is 10 to the power of 0. That's 1. So for example, the Earth is somewhere sort of on this type of orbit. And you can look at the planetary mass. They've done it in units of Jupiter. So in other words, this thing right here has 10 masses of Jupiter, and then something that's heavier, and this is something that's lighter. And the Earth is obviously a lot less. But this just gives an idea of the distribution of these different ones. And now you can get way more data, and that's why I didn't try to show you how many of them have been detected, because you should look at it yourself. Take a look at exoplanet.eu, and you can see on their website they're always updating it, and you find all the newest data. It's just so cool. So whenever there's a new thing being put in, a new exoplanet, they put it in the catalog, and they tell you all the information about it. So it turns out you can see these are all the sort of ones, and you can see when they've been updated, when they were first discovered. You can take a look at one of these and say, okay, let's take a look at this one. Oh, look at it. This is its mass. It was discovered then. It has this orbital period. And you can then, this is a star that it orbits. So this is a real live sort of website that keeps track of all these different exoplanets. So if you want to check out how many there are confirmed, check this out, because it's changing every day. They're always adding new ones, it seems. And like I said, Kepler has a few thousand candidates. Now, these candidates have been detected using the transit method that I talked about before. By looking at the light of the star as it passes. The light of the star as the planet passes in front of it. But of course, when they detect it this way, they try to see a few transits. And what they try to do then is confirm its existence to make sure it's not just something like either a binary star or a star that's doing weird stuff. But what they do then is they try to confirm it with another method. For example, radial velocity method. So in the next videos, we're going to be going over this stuff in a lot more detail.